200 feet below the surface, inside a cloud of krill so dense it turns the water the color of rust. Something longer than a jumbo jet rolls onto its side and opens its mouth. For the next 10 seconds, nothing about its body works the way it does at any other moment of its life. Its throat balloons outward, folding open along dozens of accordion-like pleats until the mouth cavity briefly becomes larger than the animal's entire head was a moment before. Water and prey pour in by the ton, a wall of ocean collapsing into a space that did not exist a heartbeat ago. And somewhere inside that colossal chest, an organ roughly the size of a small car is being asked for more oxygen than the muscles around it can possibly receive in time. Along the underside of the throat, dozens of parallel grooves run from the chin back toward the belly, each one a fold of skin and blubber, pleated the way fabric gathers along a curtain rod. At rest, those grooves lie flat, almost invisible beneath a layer of smooth gray skin. Mid-lunge, they do the opposite of what skin normally does. Instead of resisting the water pushing against it, the tissue lets go, stretching and unfolding outward until the whole underside of the animal balloons into something closer to a parachute than a throat. Behind that expanding pouch, rows of baleen plates hang down from the upper jaw like the teeth of an enormous comb. Each plate made of the same protein found in human fingernails, frayed along its inner edge into a mesh fine enough to trap krill smaller than a fingertip, while letting every drop of seawater slip back out. This is a blue whale feeding. It is the single most violent, most expensive action this animal performs. And it happens hundreds of times a day, every day, for months at a stretch during the feeding season. It is also, strangely enough, the reason blue whales are the largest animals that have ever lived. Bigger than any dinosaur, bigger than any fish, bigger than anything the ocean has produced across 4 billion years of experimentation. And there is a growing body of evidence suggesting it may be the very same reason they cannot get any bigger than they already are. That sentence sounds like a contradiction, and it deserves a moment of patience, because the contradiction is the entire story. The same feeding trick that built the largest body in the history of life also appears to be the wall that stops that body from growing further. Not a wall in the dramatic sense, no single catastrophic failure, no clean line an animal simply cannot cross, but something closer to a narrowing corridor. One that a lunging body has been squeezing through for millions of years and is now, at the size of a blue whale, almost too tight to pass. To understand why that corridor narrows, it helps to leave the ocean for a moment and think about something far more familiar. Why nothing on land ever came close to this size. A land animal spends every second of its life fighting gravity. Bone has to be thick enough to support the weight stacked above it, and the amount of bone required increases faster than the amount of muscle available to move it. Double the length of an animal, and its weight climbs roughly 8-fold, while the strength of its legs, which depends on the cross-section of bone and muscle rather than on length alone, only climbs about 4-fold. Somewhere in that widening gap, the math stops working in the animal's favor. Legs buckle under their own load long before a body can approach anything close to the mass of a blue whale. This is not a rough guess dressed up as science. It is close to a hard mechanical limit, and the fossil record backs it up with striking consistency. The long-necked dinosaurs that once thundered across ancient floodplains, animals whose thigh bones alone could stand taller than a grown adult, pushed land gigantism about as far as it has ever gone, and even the largest of them, by most estimates, weighed only a fraction of what a single blue whale carries around today. Different lineages, separated by tens of millions of years and an entire mass extinction, All seem to have bumped into roughly the same ceiling. That kind of repeated failure at the same point is usually a sign that the limiting factor is physics, not biology. Water erases that particular problem almost completely. A body suspended in seawater does not need its skeleton to hold itself up the way a land animal's does. The water itself provides the support, pressing in from every direction with a force that roughly cancels out the pull of gravity. Weight in the ocean stops being a structural emergency. This is the first half of an honest answer to the question in the title. Gravity is not what stands between a blue whale and a bigger blue whale. Whatever the real limit is, it has to be something else entirely. For a long time, the assumption filling that gap was food. The ocean is enormous, krill are small and reproduce quickly, and it felt intuitive to imagine a whale simply growing until it exhausts the food available nearby. The way a garden eventually runs out of soil to feed a spreading root system. That explanation is tidy, and it is also incomplete, because it treats a whale's body as a passive container waiting to be filled, rather than as a machine that has to spend energy in order to acquire the energy it needs. A container has no running costs. A whale does, and those costs turn out to matter enormously. The clearer picture came not from studying how much whales weigh, but from studying exactly how they eat. Rorquals, the family that includes blue, fin, humpback, and minke whales, feed in a way found almost nowhere else among large filter feeders. A right whale, by contrast, swims forward with its mouth propped open at a gentle, sustainable pace, letting a continuous curtain of baleen strain plankton from the water as it glides, more like trawling than hunting. A rorqual does something closer to an ambush. It accelerates toward a swarm, twists its body, and lunges with its jaw thrown wide, engulfing an enormous gulp of the water and prey in a single, explosive motion. Loose folds of skin running along the throat, called ventral pleats. Let that gulp balloon outward to a volume that can, for a few seconds, exceed the size of the whale's own body before the animal closes its mouth. Forces the seawater back out through hundreds of baleen plates hanging from the upper jaw, and swallows whatever solid prey remains trapped behind. This maneuver is expensive in a way that ordinary swimming is not. Turning the body broadside and flinging the mouth open at speed creates enormous drag, far more than almost any other movement a whale makes, and executing it burns a striking amount of energy in a very short window of time. Researchers who spent years attaching sensor tags to the backs of whales, devices that record acceleration, depth, orientation, and the precise kinematics of every lunge, eventually built a data set covering more than 300 individual whales across 11 different species, logging over 50,000 separate feeding events. What that data revealed was that the muscular effort required for a single lunge can spike dramatically above an animal's normal cruising output, resembling a full sprint far more than a steady swim. Building a model precise enough to say any of this with confidence required years of unglamorous fieldwork. Small sensor packages, roughly the size of a paperback book and held in place with nothing more than suction cups, get attached to a whale's back from a research boat using a long pole, staying in contact for anywhere from a few hours to a couple of days before releasing on their own and floating to the surface to be retrieved. Inside each one, accelerometers and depth sensors record every roll, twist, and burst of speed at a resolution fine enough to reconstruct a single lunge frame by frame, while separate measurements, drone footage taken from directly overhead, laser rangefinders, and photographs calibrated against known reference points provide precise estimates of each whale's actual body length. Combine enough of these individual snapshots across enough animals, and a pattern starts to emerge that no single observation could reveal on its own. The pattern becomes especially clear when the smaller rorquals are placed alongside the largest one. A minke whale, barely a third the length of a blue whale, lunges well within its aerobic comfort zone every time, spending only a modest fraction of its maximum oxygen capacity during even a vigorous feeding bout, with plenty of reserve left over. A humpback, considerably larger, but still well short of blue whale proportions, runs closer to its limit but rarely crosses it. Fin whales, second only to blue whales in size, sit right at the edge, showing occasional lunges that push into deficit territory under the right conditions. Only at the scale of the largest blue whales does that deficit become the rule rather than the exception. Present on nearly every full-effort lunge rather than only the most extreme ones, laid out side by side like that. The four species look less like four separate case studies and more like 4 points along a single curve, each one a little further along the same trajectory toward the same wall. Here is where the size of the animal stops being incidental and becomes the entire point of the story. As a rorqual's body gets longer, the volume of its gulp does not grow at the same rate as its body mass. It grows faster, scaling in a way closer to a cube than a straight line. A modest increase in body length produces a disproportionately larger mouthful, because the throat pouch expands in 3 dimensions while the animal's length increases in only 1. This means that, up to a point, being bigger makes lunge feeding more efficient rather than less. A larger whale spends somewhat more energy on each individual lunge, but it hauls in a dramatically larger volume of prey for that additional cost. Size pays for itself. That single relationship is the engine behind whale gigantism. An ever-improving exchange rate between effort spent and energy gained, driven almost entirely by geometry rather than by any particular ambition on the animal's part. This is also the answer to a much older question than the one posed by the title. Why whales grew so large in the first place, when their land-dwelling ancestors, roughly 40 million years ago, were closer in size to a large dog than to anything resembling a modern whale. The lunge, once it evolved, became the mechanism. Every incremental increase in body length made every future meal more profitable than the one before it. And that feedback loop, repeated across millions of years, eventually produced an animal capable of swallowing a volume of water and krill comparable to a small swimming pool in a single motion, lasting less time than it takes to read this sentence aloud. The timing of that growth spurt tells its own part of the story. The rorqual lineage itself appears to stretch back 7 to 10 million years. But the truly extreme sizes seen today, blue whales stretching close to 100 feet and weighing well over 150 tons, seem to have emerged much more recently, plausibly within the last several million years, coinciding with the onset of ice ages and the seasonal upwellings they produced. Cold water sinking and rising along continental margins during those periods appears to have concentrated nutrients and, in turn, krill, into dense seasonal swarms exactly like the one described at the start of this account. A whale evolved to profit from an occasional enormous mouthful does far better in a world of dense, predictable swarms than in a world of thin, scattered prey. And the fossil and climate record lines up closely enough with the size increase that many researchers treat the connection as more than coincidence, even if the exact causal chain is still being refined. But feedback loops that reward growth do not usually reward it indefinitely. Somewhere, the curve has to bend back on itself, and this is where the story returns to that first image. The heart the size of a small car, straining through those 10 seconds of engulfment. Muscles need oxygen to work, and that oxygen has to arrive fast enough to match sudden spikes in demand. During an ordinary swim, even a whale's enormous heart and lungs can keep pace without much difficulty, delivering blood and oxygen at a rate that comfortably covers the muscular effort involved. But during the violent burst of a full lunge, demand spikes so sharply, so quickly, that even an animal of this scale starts running an oxygen deficit before the mouth has even finished closing. Detailed modeling of the engulfment process, built from real measurements of swimming speed, drag coefficients, and estimated muscle mass across whale species ranging from the modestly sized minke up through the blue whale itself, found that at the upper end of blue whale body size, the oxygen required during a single lunge can run roughly a fifth higher than what the animal's circulatory system is capable of supplying in that same instant. The muscles keep contracting anyway, drawing on stored oxygen bound to specialized proteins in the tissue and shifting partly into anaerobic metabolism. The same biochemical fallback a human sprinter's legs rely on during the final stretch of an all-out run. And just like a sprinter, the whale pays that debt back afterward, gliding or resting briefly, breathing at the surface, letting its blood chemistry reset before its body's ready to commit to another full-effort lunge. At smaller body sizes, this deficit barely registers. A young whale, or an adult toward the lower end of the species range, can lunge comfortably within its aerobic limits, with a real margin of spare oxygen-carrying capacity left over even during the most demanding part of the maneuver. As body size climbs toward the upper reaches of what blue whales actually achieve, that spare capacity narrows steadily and eventually disappears altogether, replaced by a modest but very real oxygen debt on every single full-effort lunge. Extend the same model further, toward a hypothetical whale even larger than any blue whale ever measured. And the debt widens further still, curving toward a point where feeding itself would begin to threaten the animal's ability to recover in time to feed again. No animal can profitably spend more energy chasing food than that food is worth once caught and digested. Past a certain size, the very maneuver that made rorquals the most efficient bulk feeders on the planet begins to shift from a bargain into a liability, one lunge at a time. None of this happens by accident either. Before any lunge, there is a search. Krill swarms are not spread evenly through the water column. They gather in dense, shifting layers that rise toward the surface at night and sink back down into darker, colder water during the day, tracking light levels the way a curtain tracks the sun. A blue whale spends much of its foraging time diving through that moving layer, sometimes hundreds of feet down, assessing density before committing to the enormous cost of a lunge. Dive after ordinary dive is comparatively cheap. A controlled glide down and a controlled glide back up. The lunge itself is reserved for the moment the whale finds a patch worth the expense, thick enough to justify spending part of its oxygen reserve on a single bet. Whales appear to return to the same general feeding grounds across years and even across generations, suggesting a kind of learned geography passed down through repeated use rather than rediscovered from scratch each season. One more reason a shift in where dense krill can reliably be found matters so much to an animal whose entire size depends on finding it. That is the shape of the answer promised at the start. Not a wall built out of gravity, since gravity was never really the obstacle in open water. And not simply a shortage of krill drifting somewhere out in the dark, but a narrowing margin between what a lunge costs an animal in oxygen and muscle, and what a body is physically able to supply in the exact instant the cost comes due. Bigger brought efficiency for millions of years, right up until efficiency ran headlong into the hard limits of blood volume, muscle chemistry, and oxygen delivered in real time rather than on average. The blue whale, as it exists today, appears to sit almost exactly at the point where that particular margin runs out. It is worth being honest about how solid this picture actually is, because it would be easy to present it as a settled fact carved permanently into the biology textbooks, and that would overstate what is currently known. The oxygen deficit model rests on careful, painstaking measurement and computer modeling of drag, muscle mass, and swimming kinematics gathered from wild animals that obviously cannot be brought into a laboratory and asked to lunge on command under controlled conditions. It fits the observed size range of living rorquals impressively well. Closely enough that few researchers in the field seriously dispute it as the leading explanation. But a leading explanation is not automatically the final word, and other contributing factors likely play supporting roles rather than sitting entirely on the sidelines. Some sense of scale helps here, because numbers this large stop meaning much without something physical to hang them on. The tongue alone, when fully extended during a lunge, can weigh close to as much as an adult elephant, folding and unfolding inside a mouth cavity large enough that a small group of people could, in principle, stand inside it. The heart beats only a handful of times each minute during a normal dive, slow and deliberate, before speeding up sharply the moment the whale surfaces to breathe. None of these numbers exist for their own sake. Each one is a direct consequence of the same feeding strategy already described, scaled up to the edge of what a living body can carry around and still move through open water with any grace at all. Consider the heart itself for a moment, independent of the oxygen question. An organ that size does not simply scale up from a smaller heart the way a photograph enlarges cleanly at any resolution. Blood has to travel through vessels wide enough, in the largest individuals, for a person to swim through. And pumping fluid through a network that size against the resistance of that much tissue creates its own engineering constraints that have nothing directly to do with lunge feeding. A heart built to handle routine circulation at this scale is already operating close to what cardiac muscle tissue seems able to sustain, leaving little additional capacity in reserve for a body that might want to grow larger still. Reproduction adds its own pressure from an entirely different direction. A pregnant or nursing blue whale faces sustained energy demands that dwarf almost anything else in the animal kingdom. A calf, still nursing, can gain weight faster than nearly any other creature on the planet, fueled by milk so rich in fat that it barely resembles milk from any land mammal most people would recognize. Supporting that kind of growth requires a mother's body to funnel an enormous, continuous share of her own energy budget toward another animal entirely, for months at a stretch, all while her own feeding schedule and migration patterns continue largely uninterrupted. A body even modestly larger than a blue whale's current maximum would need to support an even more demanding version of that same reproductive arithmetic, on top of an already tightening feeding budget. Heat presents a quieter but equally real constraint. As a body grows, its volume increases faster than its surface area, which is generally an advantage in cold water. Since a larger body loses heat more slowly relative to its mass and stays warmer with less metabolic effort. But that same relationship works against an animal engaged in an activity as violent and muscularly intense as a lunge, because all that internal heat generated by burning fuel at a sprint-like rate has to go somewhere. And a body with proportionally less surface area to shed it through can begin to run uncomfortably warm during sustained bouts of feeding, particularly in the relatively mild waters where krill often congregate. There is a fourth pressure worth naming as well, quieter than the other three, but no less real. Skin and blubber, the layer that insulates a whale from water far colder than its own core temperature, also has to stretch and fold along every one of those ventral pleats each time the throat expands. Tissue that elastic, repeated across a lifetime of hundreds of thousands of lunges, experiences a kind of mechanical wear that smaller, less frequently stretched skin never has to withstand. It is not obvious that this places a hard limit on size in the way the oxygen deficit does. But it adds one more small cost to a ledger that, at the scale of the largest blue whales, has almost no room left for additional costs of any kind. None of these four factors, cardiac plumbing, reproductive cost, heat management, or the physical wear of repeated stretching, appears on its own to be the primary reason blue whales stop growing where they do. The oxygen deficit model built around the lunge itself remains the leading candidate, the one best supported by direct measurement and modeling. But biology rarely respects tidy, single-cause explanations, and it is entirely possible that all of these pressures are converging from slightly different directions, arriving at roughly the same ceiling by several overlapping paths, rather than one clean, isolated barrier. There is also a quieter, more unsettling implication buried inside this whole explanation, one that has less to do with anatomy and more to do with simple arithmetic. If the ceiling on blue whale size is set by a ratio, energy gained per lunge divided by energy spent per lunge, then that ceiling is not a fixed number handed down by biology alone. It moves with whatever sits on the other side of that ratio. How dense and reliable the krill swarms happen to be in a given ocean, in a given season, in a given year. A whale evolved around swarms thick enough to make one expensive lunge genuinely worthwhile. Gets to operate comfortably near the top of its size range, close to the edge, but still on the profitable side of it. A whale facing thinner, more scattered swarms, the kind produced by warming surface water, disrupted upwelling patterns, or heavy commercial fishing pressure on krill stocks, gets less reward for exactly the same cost, and the equation that once justified an enormous body starts quietly working against it instead. In other words, the same relationship that explains why the blue whale grew to the very edge of what a lunge-feeding body can support. It also means that edge is not a permanent fact about the world, fixed for all time the moment the species evolved. It behaves more like a peak, balanced on a knife's edge between two competing costs, held in place for now by ocean conditions that have been remarkably stable across recent geological time, and are no longer guaranteed to remain that way as the climate continues to shift beneath them. None of this should be read as suggesting the blue whale is fragile in the dramatic sense that word usually implies. This is an animal that has survived repeated ice ages, shifting coastlines, and the near total collapse of its global population during a relatively short and brutal period of 20th century commercial whaling, when factory ships equipped with explosive harpoons hunted the species across every ocean it inhabited, moving from one hunting ground to the next as each population in turn was driven toward collapse. Within only a few decades, the global number of blue whales fell from a population that had likely stood in the hundreds of thousands, down to a small remnant scattered so thinly across entire ocean basins that individuals sometimes struggle to find each other at all. A problem for an animal whose mating calls, though extraordinarily loud, still travel only so far even through water. Numbers have been recovering slowly in the decades since large-scale hunting of the species was banned. Though recovery for an animal that reproduces this slowly, with calving intervals stretched across multiple years and a single calf at a time, is measured in generations rather than seasons. The species has proven itself resilient against extraordinary pressure before, even when that pressure came from something far more sudden and far less forgiving than a shift in ocean temperature. What the energetic ceiling reveals instead is something subtler. How little slack exists in the specific arithmetic that allows an animal of this size to exist at all. There is remarkably little margin between what a lunge costs a blue whale and what a lunge gives back in return, even under favorable conditions. That narrow margin is not a flaw in the animal's design. If anything, It reads more like a kind of engineering achievement. A body built right up to the exact edge of what its own physiology can support, with almost nothing wasted and almost nothing left in reserve. There is also an older mystery tangled up in all of this, one that paleontologists have not fully resolved. The fossil record of ancient whales includes some genuinely enormous animals from tens of millions of years ago, long before the ice ages that seem to have driven modern rorquals toward their current extremes. Whether any of those extinct lineages, known today only from fragments of jaw and vertebra scattered across museum collections, ever approached the mass of a living blue whale remains an open and actively debated question rather than a settled one. Complete skeletons of animals this size are exceptionally rare to begin with, and estimating the soft tissue mass of a creature known only from partial bone is an inexact science at the best of times. It is entirely possible that the blue whale's current record stands unchallenged by anything that came before it. It is also possible that some other giant, lost to time and incomplete fossilization, once came close and simply left too little evidence behind to prove it either way. Ocean sediment does no favors for large skeletons. A whale that dies at sea is far more likely to be scavenged, scattered, and buried unevenly across the seafloor than an animal that dies on dry land and has some chance of being covered quickly and preserved intact. Every fossil whale reconstructed today is, in some sense, a guess built from a partial hand of cards. And the true range of sizes that ever swam through ancient oceans may simply be unrecoverable, no matter how careful the science gets. Return, one more time, to the lunge itself, now carrying everything gathered along the way. The whale rolling onto its side inside that krill swarm is not simply eating a meal the way a smaller animal might graze through an afternoon without much consequence either way. For those 10 seconds, it is spending nearly its entire body's reserve capacity on a single, calculated overdraft, betting that the swarm ahead is dense enough to make the resulting debt worth taking on. Get that calculation right, consistently, across a lifetime of thousands upon thousands of individual lunges. And the result is the most efficient bulk feeding strategy any animal has ever evolved. Wrapped around a body that dwarfs every other creature the planet has produced across the entire history of life. Get the calculation wrong too often. Through a body pushed just slightly past what its physiology can support, or a swarm that turns out to be just slightly too thin to justify the cost. And the debt stops being one the animal can reliably repay. Nothing in the physics or the biology forced the blue whale to grow to precisely this size and stop there by some kind of inevitable design. Bodies do not aim for a ceiling. They simply keep growing for as long as growing keeps paying off, and stop generation after generation, wherever that stops being true. Nothing is forcing it to remain at exactly this size forever either. Immune to whatever changes ripple through the ocean around it in the decades and centuries ahead. A ceiling defined by a ratio of costs and rewards is, by its nature, a moving target rather than a fixed monument. And the same equation that once pushed this species toward its current extreme could, under different ocean conditions, just as easily begin pushing it back the other way. What the evidence currently points to is an animal sitting right now at almost the exact point where one of the most successful feeding strategies in the history of life finally runs out of margin. Not stopped by some external ceiling imposed by the ocean itself, but by numbers working themselves out quietly, lunge after lunge, inside its own enormous chest. Somewhere beneath the surface, at this very moment, that calculation is running again. A body built to the edge of what its own physiology allows. Rolling toward a swarm, betting everything on a few seconds of controlled excess. and trusting that the water ahead holds enough to make the debt worth taking on one more time.